All right, we're now recording. Let's start from the current slide. And I'll also get my pen color done, which usually I forget to do. So I'll do that. But before we get started on that, let me go through these. And you've both heard them before, but the people who aren't here haven't necessarily heard them. My office hours. I may have told you on Monday that I might have to be on the Birmingham campus this afternoon. Fortunately, yesterday, my physical science class, we had class, completed everything, they took their test. We didn't have the lab because the lab was moved to Thursday. It's the last chapter, so that we didn't have a lab on, so there wasn't anything else to do, so they got to go without a lab period Tuesday, yesterday. They'll pick up one tomorrow, okay? So that doesn't sound like it has any influence on the class, but it does on my office hours. What happened was, because I got out early yesterday because I didn't have a lab, I was able to make the trip over to Birmingham and take care of the things I needed to yesterday rather than waiting till today. So that means I will get to stay on this campus from 3:15 after this class is over with until 5:15 or later. Now, why do I say or later? Because those students in that first mini-term class, it's their last class tomorrow, they turned in that much late work. And, well, plus the test that we took, and one person took the final early because he wouldn't be able to be here on Thursday, tomorrow, to take the final. So, anyway, I got bunches, oodles of grading to do, and I want to get it all done before tomorrow if possible. So I'll probably stay late tonight and get as much grading done as possible. So I will be here not just through Jonathan here, not just till 5:15, but probably later. But starting with tomorrow, my office hours don't get extended, they get reduced. Normally on Thursdays, I have office hours from 10:45 until 12:30. However, tomorrow I've got to go to the Birmingham campus, pick up the vehicle, leave it soon after 10:45 as I can, pick up the vehicle that will be taking the students to the Channel 13 Weather Center at 12:30. So it's going to take me at least 30 minutes to get over there, around 30 minutes to get over there, a few minutes to get check out the vehicle, and then about 30 minutes to drive back. So probably won't be back on this campus before 11:45, maybe closer to 12. And so anyway, my office hours will be shortened to be between 11:45 and 12 and 12:30. Okay. And then I'll be in class the rest of the time. We're going on the field trip, coming back from the field trip, they'll be taking their final, and then I imagine they'll be through with the final by 3 o'clock anyway. So if so, no, I'm sorry, by 4 o'clock anyway. So I will be able to make up some of those office hours because I'll be here until 5:15. But it won't be at my normal time, it will be later in the day. Then on Friday, okay, keeps coming. I have my annual physical Friday morning at 8. Normally I'm on the Birmingham campus at 7:45. I won't be. I'll be at the Kirkland Clinic at 7:45, be preparing for my physical at 8. Hopefully it'll be over by 9. Hopefully that means I'll be back on campus by 9:45 or 10 o'clock if everything runs well. Now, if there's any glitches, delays, other things, I might be later, but hopefully I'll be there before 10 o'clock. Okay? And then next week, hopefully it'll be more normal. Wait. Let me just tell you about next week. My office hours change on Tuesdays and Thursdays of next week. The reason is my first mini-term class went 12:30 until 5. It was a mini-term class, so it's 2.5 hours class, 2 hours of lab every day. Second mini-term class doesn't start at 12:30. They're automotive students, and they are in class until 1, so we start my class at 1:15, which means I'll be going 1:15 until 5:45. Okay, so that opens my office hours up to 10:45 to 1:15. So I do have longer office hours on Tuesday, Thursday, but I'm here later in the day. And Matt is here. Okay, but that will be next week. I don't know if I'll get the syllabi changed or not. I'll try to, reflecting the second mini-term office hours, but I have so much to do. I don't know when I'll ever get to do that. So just know it ahead of time. That's the case. All right. Any questions on anything we've covered so far? All right. The other thing I wanted to say, and some of you have responded already. In fact, let me see. In this class, uno, only one person has turned in a paper yet, and zero, as opposed to uno, zero have turned in the first test. So please try to get that first test in. Oh, you just turned in your papers. 2 people have turned in papers now. Next week is the first week of second mini-term, meaning just the first week after midterm. And on the academic calendar, they have posted there, next week is when midterm progress reports are due. Now, sometimes they forget to open it, but other times they do, and they want to have everybody responding to it. Well, if they do, I've got to respond. Any people who don't have an A or B at midterm, A, B, or C at midterm, I have to respond. And if I don't have any work from you, guess what? You don't have an A, B, or C, okay? So please get it in. 2 of you have turned things in. Hopefully the others will either get a paper into me, a test into me, or both into me. And you got this weekend to work on them, so do it. You can get it to me today, tomorrow, Friday, even better, but next week will be fine too. I'll just put off doing it until the last of the week, if I think something's coming. All right, the 2 folks who aren't here, that's the main people I'm saying this for. I need to have either a research paper back or your first test back next week if possible. All right, any questions? All right, let's pick up. I think we were on in chapter 2, first order differential equations, section 2.4, exact equations, and I think we're at the top of page 67, example 3. Is that where we are? Seem about right? Okay. So example 3 is this. Solve this. dy dx is equal to xy squared minus cosine x sine x divided by y times 1 minus x squared. Okay? With the additional condition, y of 0 is equal to 2. Okay? Now, how would you go about solving that differential equation? What would be the things that go through your mind? Okay, nothing's going through your mind. Is that what I understand? Okay. All right. First thing that pops into mind is this separable? Can you separate the variables? Well, yeah, I can get the dy over here, the dx over there, and I can get this y over there. I can leave these x's and those x's over here. But what do I do with that one? I don't think there's any way in the world that I'm going to be able to separate that well. So separation of the variables, I think, is out of the question. Okay, linear, solve it by the integrating factor. Ooh, that looks pretty painful to me. So let's say we'll pass on that one. So can we solve it as an exact? Well, we don't know yet. What is the general form for the exact differential equation? Which, by the way, is what this section is named, so maybe that's what they're hoping we'll do. The exact differential equation needs it written in differential form, not derivative form. So basically what I would do is multiply both sides of the equation by the denominator here. that would leave you y times 1 minus x squared dy, and then in differential form, the dx would come to the other side, and that would be xy squared minus cosine x sine x dx. Okay? Now that's not quite exact equation form. If you turn back to page 64 in that definition, you'll see you need functions of x and y times dx plus functions of x and y times dy. Okay? So, depends on which way you want to go with this. If I were doing it, I would move this to the other side. And that's adding that, or subtracting this, adding that to both sides. So in other words, it winds up being cosine x sine x minus xy squared dx plus y times 1 minus x squared dy, okay, is equal to 0. That's our standard form as you see on page 64. Okay? Can you look at that and tell me whether we can solve this using exact methods? You can. Very good for you. How did you see that? Okay, this is your m of xy. Is that what you're saying? Times dx plus, good, n of xy dy equals 0. Does that guarantee you can do it? There is a condition that must be met. You must test. Yes, you must test first. That's in theorem 2.4.1, which is just below that definition for the exact equation. And what does that say? This, remember, is your m of xy, and this is your n of xy. What does that condition? Say again? Yeah, the partial of m with respect to the opposite one, y, must be equal to the partial of n with respect to x. That's it on the bottom part of page 64. So let's do those and see what they come out being. What is the partial of m with respect to y? And frankly, folks, I don't see how it's going to happen, but let's see. What does that give us? Oh, yes, I do. Okay. Partial of this thing with respect to y. How about that first one? Cosine x sine x. Partial of that with respect to y. 0, because it has no y dependence at all. It's just like a constant. Okay, the second part, partial of that with respect to y, would be minus 2xy. Okay. Now, let's see what the right-hand side does. If we take the partial of that with respect to x, well, let me rewrite this slightly, y minus x squared y. Wouldn't that be correct? Take the partial of that with respect to x. How about that first term? 0, because it doesn't depend on x. Second term? Minus 2xy. Ding, 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 ding. That sure enough does. They're equal to each other. We can use the direct, exact representation, okay, the techniques. Okay, if we're going to do that, then we have to remind ourselves what we want to happen, okay? Now, the method of solution here is let's first say that we think there must be some function f for which the partial of f with respect to x dx plus the partial of f with respect to y dy is equal to some constant. If that's the case, then we can go. So we're through with this test, so I'm going to get it out of the way just to keep it from confusing you. Okay? You saw what the test was. You saw it pass. Let's get rid of it now because what we're going to do from this point on is different from what we just, the test. Okay? So let's move on. So we want there to be some function f such that the partial of f with respect to x is the same as this m of xy. Cosine x sine x minus xy squared. Okay? So write that as a differential, and you have df is equal to cosine x sine x minus xy squared dx, and integrate both sides. So our function f would then be, okay, what's the antiderivative of cosine x sine x? And I can think of at least two ways of expressing it. What do you think it is? Say again? I thought I heard you say 1/2. Did you? No. Huh? It's not 1 over cosine. Let's try this. Cosine squared x over 2. Let's see if that would give you that. If you're integrating that, then if you differentiated that, you should get that, right? So if you take the derivative of cosine squared x, you get 2 times cosine x, right? But the 2 cancels this, so you get cosine x times minus sine x. I wanted it a plus, so I don't like that. Okay? Let's try it the other way. Let's put the sign in here. Okay? Now let's try that. Derivative of f would then be, derivative of this thing would be 2 times 1/2, which is 1, sine x times derivative of sine, which is cosine. So sure enough, that does it for us. Okay? Minus, now, we're taking the antiderivative of xy squared with respect to x, meaning we count y as if it's a constant. So what would that be? Minus x squared y squared over 2. Let's see if that works. Take the derivative of that with respect to x now, because that's what you're doing. It'd be 2 times 1/2 is 1, x y squared. Right? We need to go back to 1.6. We hadn't done partials, so this is something a little new for at least one of you. Okay. Now, we've integrated that except for, since this is an indefinite integral, except for, anytime you do an antiderivative of an indefinite integral, you must put a plus c, except now we're doing with respect to x, that could be a y, some function of y. And I usually use, they use g of y. So let's put plus g of y. So that's what we propose the function f to be. It's a function of both x and y. All right. Now another feature of this is that the partial of f with respect to y, we want to be your n. Well, here is our x, our f, so let's take the partial of this with respect to y. And in that first term, what's this partial with respect to y? Help me. What's the partial of sine squared x over 2 with respect to y? 0, because it has no y dependence. X is treated as a constant. So sine of x would be a constant. So sine squared of x would be a constant. So derivative of a constant is 0. But on the next term, what would you have? Partial of this with respect to y. Help me. Minus what? Taking derivative with respect to y of this term here. 2 times 1/2 would be 1. X squared y. Why not? Plus g prime of y. We don't know what g prime is, but it would be that, right? All right. Well, let's see how that ties in with our n, which n was y minus x squared y. Well, what does that suggest that g prime must be? This is our n. This is what we want this to be. So what must g prime be? This is this. No, g prime must be your y part. You see, your partial of f with respect to y is this from up there. Your n here, and we want the partial of f with respect to y to be n, so this is supposed to equal that. These parts are the same, leaving that g prime of y must be y. You see that? It's sort of like you're adding x squared y to both sides of the equation, and they go away. You're left with g prime y is equal to y. So let's solve that one. G prime, or let's write it this way, dg dy is equal to y. And write that as dg is equal to y dy. And integrate both sides there, and what do you get? G is equal to, say again? It's the antiderivative of y. Say again? Antiderivative of y. I'm going to have to go back and talk to your Cal 2 instructor. Oh, no, I can't do that. Okay. Antiderivative of y. Over 2, yes. So g must be y squared over 2. Okay, we'll just leave it like that for now. Okay. And so now we have our f function, f of xy, and that's equal to, where was it? Yuck. There it is. Okay. Sine squared x over 2 minus x squared y squared over 2 plus y squared over 2. That's the g of y right there. Okay? And this must be equal to some constant c. That's the requirement. F of xy has to equal c. Okay? That is the equation we're looking for. Now, we know that y of 0 must equal 2, so let's plug in a 0 for x. Sine squared, well, let's first do this. I'm going to change this ever so slightly to be sine squared x minus x squared y squared plus y squared is equal to 2c. Just multiply everything by 2. Okay, plug in x equals 0, and what do we get? Sine of 0? Say again? That's cosine. 0. That's gone. X squared, when that's 0. So we get y squared is equal to 2. So c must be equal to 1. Right? Y squared is equal to 2c. Sorry about that. Yeah, what am I doing here? Yeah, no, okay. But y squared is equal to 4, sorry. So 2c is equal to 4. I'm sorry, I got crossed up where I was going there. So what's c equal to? 2, exactly. So c is equal to 2. So our solution is f of xy is equal to, well, we don't need this anymore. Let's just start here. There it is. Sine squared x over 2 minus x squared y squared over 2 plus y squared over 2 is equal to 2. Multiply both sides by 2 and you get sine squared x minus x squared y squared plus y squared is equal to 4. Okay. I think that should be our solution. No, wait. All right. They did something a little weirder. They used cosine, okay? We use sine. So our answer will be a little bit off. I'm going to erase some stuff so you can see what's going on here. Is that okay? All right. Let's erase this. Erase part of the problem, which I didn't want it to. Erase another part of the problem I didn't want it to. Well, this is slow erasing, isn't it? Yeah, I can erase this. I hope I haven't erased too much. Oh, there it is. Okay, I'll erase this. Okay, this was the solution we came up with. Now I'm going to change a little bit, not too much, but just a little bit, if I can get this to finally finish erasing. Okay, getting close. There we go. All right. Okay. Let me rewrite it here. Sine squared x. I'm going to pull out a minus y squared times x squared minus y. No, minus 1. Sorry about that. Is equal to 4. Okay? Minus y squared, x squared minus 1 is equal to 4. Okay? That's, to me, a solution. The book went with cosine rather than sine. So we know that this is, what's sine squared in terms of cosine? Say again? What is sine squared in terms of cosine? 1 minus cosine squared. X minus y squared times x minus 1, x squared minus 1 is equal to 4. Okay? Now I'm going to do something a little bizarre here. Well, it's not bizarre. I'm just going to remove these parentheses because they're not doing me any good whatsoever. And then once those are removed, I see that I can subtract 1 from both sides. And then I'm going to rearrange this ever so slightly. I'm going to move this x squared minus 1 up front, but change it to 1 minus x squared. Now, there's two reasons for that. Number one is I like to lead with a positive. If I swap that over, then this becomes a y squared here, minus cosine squared x, and that's equal to 3. Now, if you look at that answer and look at what they've got, except they left the y squared in front, that's fine too. And by the way, the original problem was a y here and a parentheses there. Okay, so if you put the y squared in front, that's fine too. Y squared times 1 minus x squared minus cosine squared is equal to 3. That's the same answer we have. Okay? What they've done is combine those two terms, the last two together, y squared times 1 minus x squared, and then change the sine squared to 1 minus cosine squared. Yeah, this answer and that answer is very close. Okay? Notice there's no parameter here, no c like we've been having. Why? Because we had an initial condition that allowed us to evaluate that c. Make sense? Now, if you remember from the last section, which seems years ago, okay, that the left-hand side of the linear equation can be transformed into a derivative when we multiply by an integrating factor. The same basic idea sometimes work for non-exact differential equation. That is, sometimes it's possible to find an integrating factor mu of xy so that after multiplying the left-hand side of the thing then becomes an exact differential. In an attempt to find mu, we turn the criterion from 4. Remember that was what we checked. Partial of m with respect to y, partial of n with respect to x. Set those equal, see if they're equal to each other. Now we have, you have to use the integrating factor times m, and the partial of that with respect to y, and compare that with the partial of that integrating factor times n with respect to x. Okay. By the product rule of differentiation, the last equation is the same as a much hairier looking equation. The difficulty here is to determining the unknown mu from equation 9 is that we must solve a partial differential equation. Since we're not prepared to do that, we make a simplifying assumption. Suppose u is a function of only one variable. So let's first try x, see if that works. If it doesn't, then try it with respect to y, okay? And it goes on and on. Frankly, if you have to do all that much work to it, just do integrating factor, okay? I don't see any reason to try to do this. Now, unless it isn't a linear equation. And guess what? This one wouldn't have been a linear equation, would it? Because you got a y squared in there. Well, wait a minute. I think you still could have gotten this to be 1, because this one over y would go to y, and that one over this thing would have had a y in it, but you could multiply and get the y back on the other side, and then you'd have your x's alone. I think you could have gotten this. So rather than try to fiddle around with it, try to give it a different method. They give the formula here. If you need to go back and do it, okay? They give you the two equations 13 and 14 on page 68. Now, you don't have a book yet, do you? Okay. Let me write those down, okay? It all gets down to this. You have m sub y. Remember, we did that before. Okay. Make sure I've done it right. Yeah, m sub y, when we're doing our test, minus n sub x, okay, divided by n. That's the n by itself. If this thing comes out to be a function of x alone, let's see. Let's call it mu, not f. If this thing, when you do that, you do your m sub y minus n sub x. Remember, that was your test. If they're equal to each other, you didn't have to do anything else. If they weren't equal to each other, if the difference between the two divided by n, which is a function of x and y, if this is some function mu of x alone, if that's the case, then the integrating factor, that mu sub x, and really I maybe shouldn't have used, let me see, because that's not necessarily the case. Let's call it a function of x, okay? Then the mu sub x would be this. E to the integral of this thing here, m sub y minus n sub x over n dx. If it is a function of x alone, then you can take the derivative of that. If, however, the m sub y minus n sub x over m, okay, sorry, I don't think it matters here, but I'm trying to keep in the same way the book does it. If n sub x minus m sub y over m is a function of y alone, okay, then your integrating factor is a mu of y, and that would be e to the integral of n sub x minus m sub y over m dy. If that thing is a function of y alone, then do that. Okay? Now, Buddhists are giving us an example, so we're going to take that to the bank. See if it works. Remember what I just put up there. Here's a nonlinear, so we wouldn't be able to use the linear technique. xy dx plus 2x squared plus 3y squared minus 20 dy is equal to 0. Now that looks like it's the right form for exact, right? But what do we have to do? Test it. Okay? So what's the test? Remember, this is your m. This is your n. What's that? No, the whole expression's your n. Yeah, right. So what do we do? What's our test? Partial of m with respect to the other one, which is y. And what would that be in this case? Pretty easy, isn't it? Not 0. 1. No, not 1. X. Taking the partial of this thing with respect to y, the y goes to 1. X acts like a constant. If you take it with respect to one variable, the other variable is held constant. Treated like a constant. So that's x. Okay? And over here, we do what? Partial of n with respect to x. And what would that be? First term? Second? 4x. All right. And the rest of them? 0, 0. Exactly. The trouble is they're not equal. Not equal. Now, it seems like to me the way to go on this one is to do n sub x, that's that one, minus m sub y, which is that one, divided by m. Remember, it's always, if you look back on the other page, those conditions are the one that you subtract, the m or n, but it's a partial, but you divide by that function, okay? And this, I think, will work out quite nicely, won't it? Because that would be 4x minus 3x divided by, no, minus x. I'm subtracting already. Sorry about that. Say again? Yeah. 3x, and you divide it by your m, which is xy. Remember, that's your m. Okay, so this will be 3x over xy, which is going to be 3 over y. Is that a function of y alone? Yes. Okay. Since it is a function of y alone, what do we do with it? Your integrating factor of y then is going to be what? E to the integral of 3, yeah, that thing right there, that very thing we calculated, which here is going to be 3 over y dy. Now, what's the integral of 3 over y dy? Say again? Okay, this will be 3 times the natural log of y. Now, if I write that in a slightly different form, that would be the same as what you do with the thing constant in front. Move it to the exponent. Rules of logarithm, that would be the same as log of y cubed, right? So this will be e to the ln of y cubed. What will that be? Look, y cubed, exactly, because the e undoes the log undoes the e. So that gives you y cubed. That's your integrating factor. What do you do with it? You multiply it by each of your original things. So this now becomes x, y to the fourth dx, right? Plus 2x squared y cubed plus 3y to the fifth minus 20y cubed dy is equal to 0. Y cubed times 0 is still 0. Okay. Now we really probably ought to do our test again. This is our new m now. And when you take the partial of this thing with respect to y, what do you get? You want to do it? Partial of that thing with respect to y. Not that hard. Did you? Oh, x is in there for sure. Partial of the rest of it with respect to y. 4 y cubed. Yeah. Okay, let's do this one over here. Let's take the partial of this thing with respect to x. And what would that be? For x y cubed plus 0 minus 0, right? Because there's no x's in those other two terms. Ding, 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 ding. They're equal. You see it? All right. So now we can do our linear procedure. Our exact procedure. We don't need this anymore. So let's get rid of it. We need the space. Okay? What we do need is that. And that. We don't need this anymore. We don't need that anymore. I don't think. I sure hope not. I've already erased it. We don't need that one anymore. Or that one anymore. Or this one anymore. We've already used this, so we don't need any of that anymore. So, we're trying to do this equation. And what do we do first? Remember the technique? What do we do? It's been a long time, I realize. Maybe 15, 20 minutes. Okay. What's that? I can't hear. The partial of m with respect to. Right. Okay, that's where you're starting? Okay. We hope that there's some f, I can't hear well, sorry. It's a function of x and y that's equal to c. Okay? Now, what must be true of that? If that's going to be our solution, then the partial of that f with respect to x is going to be our new m. That's this m down here, not the one up there, this one, equal to x y to the fourth. Right? We need that to be our m. Okay? So that would then be, I'm going to write this as a derivative. It's probably not legal to, but it makes it easier to deal with, is equal to x y fourth dx. And integrate both sides, and that gives you f to be the antiderivative of that if with respect to x. A little louder. X squared y to the fourth over 2. Now that would be the antiderivative of that, but we usually have to have a plus g of y. Normally it would be a plus a c, but since we're doing partials and have other functions, independent variables in there, it could be a function of y. Because we took the partial with respect to x, which didn't mess with the y. And we're treating the y's like constants, so that's what we got. What do we do next? Take the partial of that with respect to y, and that would be what? Partial of this with respect to y would be a little louder. 2x squared cubed, very good, plus g prime of y, right? Taking the partial of that with respect to y, be the derivative of that with respect to y, because there's no x dependence there. Okay, and we hope that's going to be our n, right? And let's see, sure enough, this part matches, and what we've got left is that the g, and I'm going to write it this way, dg dy is equal to this thing here, 3y squared minus 20y cubed. No, 3y to the fifth minus 20y cubed. I can't read or write very well. Ooh, that's ugly. Okay, let's try that again. That's to the fifth. You see that? G prime of y, because these parts are the same. We don't need that anymore. Must be this part. G prime must be here. Okay? Now, that one I'm pretty sure that we can do. Let's write it as dg is equal to 3y to the fifth minus 20y cubed dy. Integrate both sides. And our g then would be, g of y would be equal to, what does that give us? Antiderivative of 3y to the fifth. 3y to the sixth over 6. So that's going to be y sixth over 2 minus 5y fourth. Okay, I think we can go with that. If I can find where it, there it is. Okay, so our f of xy is equal to x squared y fourth over 2 plus y sixth over 2 minus 5y fourth, and that's equal to that mystical little c there. Okay? Now, were there any initial conditions here? I don't think so. Okay? So I believe that may be our solution. Or, if you don't like those fractions, you could say x squared y fourth plus y sixth minus 10 y fourth is equal to some other c. 2c, you could say that if you wanted to. Anything you want to. Make that a new constant, k or d or c1, or it doesn't matter. Let's see what they came up with. Oh, they left the 1/2 in there, didn't they? Shame on them. 1/2 x squared y fourth plus 1/2 y sixth minus 5y fourth is equal to c. Sure enough, that's it. We finished 2.4. Wasn't that exciting? Okay, homework exercises. Do any of the odds 1 through 19. There's a whole passel and a half of them, but the good news is not only are the answers in the back of the book, but they also the answer to selected odd number problems begin. Oh, I'm sorry. They don't have that. Sorry about that. They begin in the back of the book. Sorry. Selected odd number problems. I think most of those are back there. Then do any of the odds 21 to 25. Do 27. Do 29. And do any of the odds 31 to 35. Do 37. Do 39. Now, most of the times these discussion problems are not in the back, but there's some pretty interesting little mathematical modeling here. The falling chain problem. I've actually lived through one of those. I don't know if you're interested in this or not. When I was in the Navy, the ship I was on was getting ready to go into the yards. You know, they go in about every 4 to 6 years, something like that. And they update everything, update systems and fix things and repair things that are being broken and stuff. So before you go into the yards, they have, and Navy abbreviates everything, an INSURV. That's inspection and survey. So a team comes out and have you do all sorts of tests on all sorts of equipment and see if all the equipment works as the way it's supposed to. If it doesn't, then they're going to try to take care of that in the yard. Okay, every ship in the Navy has, on either side of the bow, a great, big, huge, heavy anchor weighing many tons just by itself. And the anchor is held by links of chain that probably weigh at least a ton or two themselves, each link. Okay? And this thing is hanging there out the hawse pipe, they call it, and it goes from somewhere below deck. The chain runs around to below deck, and there you have great big spools with this chain on it. And you have what they call an anchor windlass. Now, most of the time you operate this with machinery, okay? But in case the machinery falls apart or electrical power goes out or something like that, if you have to brake that by hand, they have a way to do that. It's called the manual brake. So we were up on the forecastle, that's the forward part of the ship. I was the assistant first division officer. I was the assistant first lieutenant was what the title was, which was, and also the third division officer. But I was up there in that capacity with my phone talker, and the inspection survey team was there, and the people from the first division that were there operating the thing. They said, let's test the manual brake for the anchor windlass. So they said, okay, let it go, and when we say stop, stop it. So you let it go, and the chain is marked every so many fathoms with a yellow link, a green link, then a yellow link so many fathoms later, a red link. You don't want to go past the red link. Okay. So they said, release the anchor. So they did. And when they saw the green link go by, they said, stop it. So the guy out there started turning that anchor, the manual anchor windlass brake, as hard as he could. He finally got it to stop. I mean, It was a lot of work, but it stopped. So, well, we may need to look at that, but we're supposed to do it 3 times, so let's do it the second time. So he released the brake, and it started falling again, and then very soon the yellow blink went by, and he said, stop it. So he went to doing, man, he was all the strength in his body, he finally got it to stop. Okay, that took a while. By this time, the anchor was in the water, and bunches of heavy links. So it was getting heavier and heavier and heavier, forced downward here. A little bit of buoyant force, but not very much, okay? So he said, we need it one more time. And they said, that hardly stopped it at all. Yeah, no, we need it one more time. We're supposed to do this 3 times. Okay, so we told the bridge what they said. Okay, release it. So he released it, and almost immediately the red one went by. Stop it, stop it, stop it. So he started cranking down as hard as he could. Nothing was working anymore. It wasn't even slowing it. It was going faster. And by this time, dust was all over the place. You couldn't see anything. And it was just falling faster and faster, making enormous noise. And in the Navy, they have this term called the weakest link. You probably heard that as a phrase. What that is the link that, the last link between the chain and the board in the ship. They make that a weak link. The reason, if that should go away like it was running away on us, then that breaks rather than pulling the board out of it, and just wrecking the whole ship. So they always have the weakest link there. Hopefully you never get to it. We got to it. And sure enough, that thing broke somewhere down there, but everything was happening so fast, and it was so loud, everything was so loud, dust everywhere, it was rust and paint and everything else. And then all of a sudden, out of the house, out of below deck, came the end of it, and went, wow! Whoa! It went, whop, 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 and it went down the thing. Well, the first place it walked on the deck, now the deck is about 6 to 8 inches thick of solid steel. Okay? That place that first walk that went down, the end of that chain hit that deck and left a big size serving dish crater there, indented that much. That was about 1.5 feet from where I had been standing. I didn't even realize, it was happening so fast, so much noise, so much everything, so much dust. I knew the end came. I didn't know it had hit, and didn't know it would hit anywhere. I looked down, and there, just a short distance away from my foot, was this indentation. If I had been standing there, nothing would have told me not to stand there. Then I would have been in the indentation. It would have been pretty brutal. Or if just my foot would have been there, no more foot. Okay. What's more is we had just had installed within the last year celestial navigation system. Not celestial. Satellite navigation system. Okay, which was a precursor to what everybody has now with GPS. This was the early version of GPS, the military version, which was quite good. Okay, and that antenna got really wrapped pretty badly. In fact, it may have been just enough to divert that from hitting my foot, because it may have been that it was coming right at me, but the antenna deflected it just enough. I don't know. So I looked around to my phone talker to explain he had gone over the side, not all the way over, but he was on the other side of the thing hanging on for dear life, because he didn't know where that was going to end up. He was quicker reactions than I had. Yeah, but anyway, I helped him back off this right side of the thing. So yeah, that problem is an interesting problem. Falling chain problem. If you're that interested, go for it. Okay, you probably aren't. But old sea story, okay? So let's move on to 2.5. Okay, 2.5 is solutions by substitutions. Okay? Now, let's see the little introduction here. We usually solve a differential equation by recognizing it as a certain kind of equation. What's the first kind we look for? 2.2. Easiest thing to do? Separate them. If you can separate the x's and the y's, you get the x's with the dx's, the y's with the dy's, then you can integrate both sides and you got your answer, right? Okay? Linear, that's that certain form that you do the integrating factors, u, okay? Or exact, that's the one we just did. So that's 2.2, 2.3, 2.4, okay? And then carrying out a procedure. My calculus professor called that trick. If the trick works several times, call it a method. So yeah, we follow those things, okay? Consisting of an equation-specific mathematical steps that yields a solution, okay? But it is not uncommon to be stumped by a differential equation. What an understatement, okay? Because it does not fall into one of those classes of equations that we know how to solve. Separable, linear, or exact, okay? The procedures that are discussed in this section may be helpful in that situation. So here's what we're going to try. Often the first step in solving a differential equation consists of transforming it into another differential equation by means of a substitution. Almost sounds like your integration technique, doesn't it? Okay? For example, suppose that you wish to solve the first order differential equation. My pen is all tight. There we go. First order differential equation, dy dx is equal to some f of xy. Okay? Now, if there's a substitution, and let's just say that this is not separable, this is not linear in the form you can solve it by integrating factor, and it's not in a form that your test for exact is going to work. You can write it as an exact, but you can't get the test to do, not even with an integrating factor. Okay? So, let's just suppose they can. All right. So, what if we choose one of these variables, like maybe y, let's say y is equal to some other function, and let's call it, I'm trying to use the same thing they do, g of x and u, okay? Not y, but u, okay? Where u is regarded as a function of the variable x alone. So y is now a function of x, and some other function u, which is regarded as a function of the variable x. If g possesses the partial derivatives, first partial derivatives, then the chain rule says this. Remember, this is what y is. dy dx would then be the partial of f with respect to x oh, wait a minute. G, I'm sorry, G, okay. Partial of G with respect to x, okay. Okay. All right. Times dx dx, well, we know what that is 1, okay. Plus, the second part is the partial of G with respect to u du dx, okay. Now, let's write that a slightly different way. g sub x, that's partial, that means partial g with respect to x, and that's as a function of x and u. Okay, this is ugly. Okay. All right. Now, they've kind of skipped some steps here which would make it clearer, but I think this would have done it. F is now a function of x and u, which would then be g. That's not really clear either. They just jump to here of x and u. Okay. I thought I could make it somewhat clearer. I think maybe it does a little bit. Okay. Let me get that again. I erased the wrong one, sorry. Okay. Okay. So you change the F because you're coming up with a y as a function of g and u. So anyway, you get this. I don't know if that's helpful or not. Dx is just 1. Plus the g sub u, partial of g with respect to u, times du dx. Okay? Now, you still got your dy dx here, but you don't have any y's on the other side. And this is what I was trying to do before, and they do not know how to write it, so it makes a lot of sense. What they're saying is true, but they're skipping so many steps. So this is the left-hand side. The right-hand side becomes this. Going back to here, this is your dy dx, and that's your f of xy. And this is what I was trying to do before, f of x, g of x and u. I keep wanting to put it in the wrong order. Okay. That's what I was trying to show above. Okay. But they skip around, don't do it, and then bring it back in. Okay. Now, the whole purpose of doing all this manipulation. Now you notice here you've lost the y completely. Now we have partial of g with respect to x, g is a function of x and u, partial of g with respect to u, du dx. And I forgot to put this is also x and u here. Partial of u, or du dx, because that's a derivative there. Okay? And that's all equal to some function of x and g of xu. So you don't see any y's in there anymore. Okay. Now, what we're wanting to do is solve this for this, du dx. If you can get everything else on the other side, then you're okay. And that du dx, now you've got the f of x, blah, 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 minus the g of xu, divided by gu of xu. You've got all that over there on that side. All this adds up to, or combines to be, some big function of x and u. Okay? Some capital F of x and u. Now, if we can determine a solution of u is equal to some function phi of x, how many different ways are you going to express this? Of that last equation, then the solution of the original equation is y is equal to f of phi, x comma phi of x. Because we said y is a function of x and u. Okay? So why not leave it u? Why make it phi? I don't know. It seems like they just do too much in there. Now, we're out of time, aren't we? So we'll start next time with the homogeneous equations on page 71. Okay? So we got finished with 2.4 finally. We'll get started on 2.5. It's a relatively short section, so I hopefully can finish it next time and move on to 2.6, numerical method. Okay? We're just going to do a quickie on that one, and then we'll be through with chapter 2 and have another test, which is another reason, get your first test in, because soon there's going to be a second test.
Can you tell us, like you normally do, the sections that the problems came from on the first test?
I'll try my best, but some of them cross over sections. Okay. Let me see if I have. Okay, here's your first test. It's a one-pager, isn't it? Yeah.
Yes, sir.
Okay. So let me go back to chapter 1. And like I said, a little bit of a problem is that basically 1, I think, comes from 1.1, I believe. And, I mean, please don't make that any more difficult than it is. All you're doing is taking the derivative of what's in there, of that function there. And that may even come from before the section. That's what I mean. Let me just see. I think that's just reminding you of how to take a derivative. And that would be like it actually was before 1.1, but certainly if you did 1.1, you did that kind of stuff. Now question 2. Again, it's just taking the derivatives. Take your first derivative, take your second derivative. That's basically earlier, before. But then what it's asking you to do is come up with a function, and that's what I'm trying to see. That the third part of that is thought that was in 1.1 as well. Yeah, I believe it is. I just can't see it right off the top. It's just basically doing manipulation to combine your y prime, and your y double prime together so that it's equal to 0. Okay? And I don't know where that actually was, but that's all you're doing there. Number 3. That's kind of like 1.1 too. Number 4. Okay, this was implicit solutions. Yeah, this is 1.1 as well. It's like example 5 on page 7, I think. Okay? Not the same, but similar. Okay, slope of the tangent line think that comes from what I would say before this course, you know. That basically was Cal 2, 1, 2, or 3, somewhere in there. So Cal 1, in fact. Okay, number 6. Yeah, I think that's in 1.2 perhaps. Okay, I think so. 6 and 7. Let me just see. It may be in 1.3. No. It's 1.1 or 1.2, I believe. Okay. Because these are big sections. There are only 3 of them. Okay, don't get too bogged down. 6 and 7, they give you an equation, function. Y is equal to, they give you that second. Then take the take the first derivative, then the second derivative, then plug that in, combine it with y, which you have here, and verify that's equal to secant x. I mean, that's what it's saying. It's kind of from all 3 sections, kind of. Okay, and that's with 6 and 7. 7 just a lot more involved because you have logs and cosines of logs and logs of cosines and logs of products of logs and sines of logs. I mean, it's a bit involved to take those derivatives, but you just take the derivative of the second part and take the second derivative of that part and then verify that those two are the same. Now, can you get all this on the line? Probably not. So use the back of the page or extra sheets of paper, whatever. Number 8. And again, it's almost the same type thing. Here you have an equation. This again is the implicit. And the implicit is, I think, back in 1.1 again. Yeah. On page, bottom of page 6, top of page 7, you know, it's just, again, a lot like that. You take the derivative, and here it's only first derivative, so implicitly take the derivative of that, the equation that follows the semicolon, that equation there, take the derivative of that, square it, plug it, and the y squared. You can solve that for y squared. You can't solve it for y, but you can solve it for y squared. Plug that back in here, see if they're equal to each other. And then the next one, number 9, is indeed from 1.2 because that's the initial value problem. Okay, so basically, the top 8 are either from earlier calculus courses or section 1.1, and 9 is the only one from 1.2, because 1.3 there wasn't really a lot I could test you on there. You know, that made a lot of sense. So I don't know if that was a good answer or not, but yeah. Okay. And I recorded